be able to get you the grades back this week. And I understand this was a very hard midterm, but it has been graded on a curve. So hopefully you'll all still feel okay about it. But out of curiosity, who thought the midterm was about the difficulty they expected? Who thought it was easier than expected? Who thought it was harder than expected? Okay, that's not so bad, not so bad. Okay, good stuff. So, and also, as I think it's been a habit in this course, and I think it's a good idea, we're gonna, in the next, I'm not sure, week or two, something like this, we're gonna actually conduct like a sort of informal poll, not like the reviews you do at the end, just to get some sort of feedback midway, even though I know we've switched instructors, but even it can be helpful for next year in addition to this year. So, so look out for that. So before I start in on the new technical content, are there any questions, just general kind of questions that you want to ask me before we get going? Yep.
Will the slides be posted ahead of time?
Yeah, the slide, oh, ahead of time? No, in a perfect world, they would be posted ahead of time, but they're usually only finished a little bit before, which makes that usually impossible. If it turns out that they're done ahead of time, I can try and do that, but it's unlikely, I'm afraid. Maybe in future years, but hopefully you won't be in this class in future years. Okay, any other questions? All right, well, let's get started. Okay, so basically a huge chunk of this course was introducing you to the idea of regression, and it was all sort of grounded on the very simplest case to start with of linear regression, right, which was this, this function here with this very simple noise, and of course then we generalize this in a number of ways, but it all kind of has this basic framework, right? And so these are all linear models, and so sometimes people get a bit confused about what a linear model is. So just to be very clear, a linear model is when it's a linear function of the parameters, as for example right here in linear regression. And so these are really a foundational class of models that you want to learn about, both because they actually are very useful in practice, and it's also a very good starting point pedagogically. So, and when we started with a Gaussian model and a linear Gaussian model, and we cast it in this sort of probabilistic framework, then we ended up with this sort of maximum likelihood estimation, or if we put a prior on and then took a point estimate, then we got into this maximum a posterior estimation. And in any case, very frequently, or almost always, we could manipulate things to look like this, right? So in the very vanilla sort of ordinary least squares, we just had this objective function. And then as we wanted to make things kind of more sophisticated with correlated noise or correlated residuals, sometimes we had to massage our objective function to look like OLS, and then once it was like that, we could kind of read it off. So these are the kinds of things that you've seen in the first month, or however, first half of the semester, let's just say. And so in all of these cases, we always got a closed form solution for the parameter estimates, right? So in this case, the parameter, for example, W, and so I apologize because there's so many versions of this course and slides, so sometimes this gets written as W, sometimes beta, and sometimes theta. If you're ever confused, please just do stop and ask me. And so in this course, they usually start teaching how you get the solution through sort of arguments about geometry and projection. And then they also say, well, actually, if you want to think about how you can get this from sort of first principles of probabilistic modeling, if you assume this Gaussian noise and you have this probability model and you set the gradient to 0 and solve, then you get the same solution out, right? But in both cases, once we get the data, then in this one-shot computation, we know the parameter estimate, right? It's just one computation and we're basically done. Now we can go use the model or evaluate the model or whatever it is that we want to do with it. So what we're going to talk about now is going to sort of richer modeling situations where we don't have just linear models. And in these cases, the optimization is not going to turn out to be so easy. We're not just going to, and it depends, I guess it's a matter of taste. Is it easy to manipulate math, or and then you'll see how we can do the other way, which in some senses maybe easier, maybe conceptually, maybe not, depending on how your brain works, but it's going to turn out to be much more difficult optimization problems, and we're not going to be able to just get this sort of one-shot, closed-form version for it. And we're going to need to do an iterative solution where we start at some guess in the parameter space, and then we're going to move in the parameter space like over a series of iterations with the idea that we're going to get to somewhere more useful and converge to a solution. Okay, but just to make sure you understand what it is and isn't a linear model, it's actually pretty easy, I think, to get tripped up about it. So just going to walk you through a few examples here. So here, the input features are like what we often call X, are the BMI down here. And this is the regression variable, that so the typical Y variable here. So can anyone tell, who thinks this is a linear model and the original feature is X? Who is sure that it's not? Okay, good, right. So if it were a linear model with original features, it would be a line, and it'd be a straight line. Okay, so far this looks pretty easy. So could this nevertheless be a linear model of some kind? I'll give you a minute to think about it. Okay, so who thinks that it could be? Who thinks that it absolutely couldn't be? Okay, good stuff, right? So of course this is the kind of stuff you saw when you sort of lifted the feature space using polynomial features and things like this. So in this case, it's a little clunky, but you can see my cursor not showing up. It doesn't show up, does it? Just realized it's not showing up. Laser pointer. Ah, there we go. Right, so up there is a sort of clunky typographical set, but it's linear in the features, where the features are BMI and BMI squared, but it is indeed a linear model, even though we don't see a straight line. Okay, so is this a linear model? Who thinks this one's a linear model? Who's sure that it's not a linear model? Couldn't it be just like the last one? I think actually you can't really answer right now if it's a linear model. You can say it's not linear in this variable here, but you can't say whether it's linear in some set of features or basis functions that you applied to that variable, right? You have no way to know. So you basically have to look at the functional form. And so this is the functional form. You're predicting mobility as a function of density, and it's certainly not a linear function of density, or obviously in any way of any features that we can see. It's some complicated ratio of stuff here. So this isn't really a linear model. And so what you can see is that nonlinear models basically give you a lot more flexibility in how you can represent the function. You can kind of do arbitrary things, right? And that's going to turn out to be useful. So just some other examples, which we don't need to go into any detail about, but just to give you some other examples, here we have some parameters theta, and then they get multiplied by an exponential function of some other parameters theta, and inside of which x appears. That's also nonlinear. And then here you have sort of like a Fourier basis kind of thing, so also nonlinear. Okay, so here is another one. In this case, what we do is we kind of have something that's linear regression. So x times the vectors w, which we see in linear regression, plus an offset. And then we're going to actually pipe it through something what we often call a nonlinearity. In this case, it's a sigmoid. So now, because I've piped it through the sigmoid, it's no longer linear again. In linear regression, this would just be the identity function here, right? It would just be a diagonal. But because I've piped it through here, again, I've lost this nice linear dependence. And it's maybe a little bit weird to think about this for regression, right? Because the sigmoid asymptotes at 1 and 0. So if you're trying to do a general regression problem that goes beyond 0 and 1, you're going to have a hard time doing it just like this. But these things do get used in regression. And in fact, this actually is essentially what we're going to learn about later, is if you were actually doing classification, which we haven't talked about, but we will in a few lectures, then you could use this as a classifier, where actually this would be the probability of the output. But you don't need to worry about that now, just kind of throwing that in there, that sometimes it's not even clear just by looking at this if you're trying to do regression or classification. Okay. And so, and just as a peek ahead also in the next lecture, we're gonna introduce neural networks. And so this is in some sense, on the one hand, we can look at this as this classifier called logistic regression, which we'll go into later on, but it's also kind of the simplest neural network for classification. Okay, and then, and in fact, a more complicated neural network is going to be when you sort of stack these things together and you compose them. But again, we're not going to get into that this class. Just trying to show you that there's a whole bunch of nonlinear models, and these ones in particular right now in sort of modern day practical machine learning in particular domains are working really well, which is, how many people took this class so that they could learn about neural networks? I'm impressed. That's good. How many people want to know nothing about neural networks because they're too hyped up? I think that's like an even call between those two crowds. Okay, right. Okay, so these linear models, on the one hand, they kind of look a little bit like toy models once you get your hands dirty with more complicated ones, but they're very powerful, they're very pervasive, and there are a lot of real world problems where maybe they're not the exactly correct model, like if you somehow knew the physical reality underlying it, it might not be linear, it might not have Gaussian residual, but that might actually get you really, really far, especially if you don't have a lot of data to estimate a lot of parameters. But on real data problems, even if you're going to do something more complicated, I would say you should always start by trying out one of these sort of simple linear models. You should never just so what people like to do nowadays out in the world is they skip that and they go to some crazy million parameter neural network and then they show how well it works. And it's not that infrequent that if you push them and you get them to actually just try linear regression, it works just as well or nearly as well. And it's kind of embarrassing if you don't know that. So anytime you're anywhere, you're in an internship, you get a job when you graduate, always try the simple stuff first because it gives you a really good idea of what's going on in the data before you jump ahead. Okay, so we're going to go through a particular example of a nonlinear model just to kind of go into some details to wrap our head around it a little bit as a pedagogical exercise. And we're going to see why we can't get a closed form solution. And then that's going to motivate us to do some of these iterative techniques, which will take up a chunk of this course. Any questions so far? Okay. So it's going to be about robot localization. And so even in this case, if we're going to assume Gaussian noise, and we're going to get a squared error, but it's, as you're going to see, we're still, and I'm going to make you maybe work out the details at home, but we'll get very close to seeing that you can't just actually get a closed form solution here, and why that is. Okay, so let's work through this example. So this is going to try to identify, and I'm told, I haven't been here long enough, so I've never taught 16A, but I'm told this is an example used in 16A. Who here took 16A? Do you remember this? Who here remembers this example from 16A? Oh, wow. Okay, so I've been lied to. Very good. All right, well, luckily nothing in this lecture depends on that, because I also don't know exactly what's in 16A. So here we are. This is a robot in the plane, like on a floor. So there's only two coordinates, right? Basically, yeah, these would be the two coordinates. And what you want to do, the task here is using some sensors. So there's going to be sensors that tell you your distance from 3 beacons. So these beacons are at fixed locations given by these L coordinates in the plane. So we know those ahead of time. That's part of this problem is you say, put a beacon here, I put a beacon here, and I put a beacon here, and you know exactly where those are because you put them there. And then you're going to be able to, as the robot's moving around, it's going to basically use some sensors that tells you how far away you are from each of those beacons. But of course, they're sensors, and so they're noisy, right? So they're imperfect. And that's where you get into some sort of probabilistic modeling. And the idea is that at any instant in time, and we're just going to think about this as one slice in time. In this lecture, we're not talking about moving through time. Just at any given instance in time, assuming that I've got these measurements, y1, y2, y3, which are noisy measurements of the robot's distance to each of 3 beacons, how can I estimate the point in the plane at which this robot lies? Does that make sense, the question? Or the problem setup? Okay. And so just, okay, that's what I just said. And now we can read it as well. Great, okay. And this is supposed to be a video that kind of does that. Is it not working? How do I make it work? Huh. Play. Plays at home. Any suggestion? Try turning it on and off. Like, go back to the cursor. How do I get rid of the laser? No, go back to the cursor. Pen, highlighter. I think, is it off now? Yeah, okay. Well, now it's something else. Let me kill it. Close it. I could open the link. That's getting, oh, this is really weird. It seems to think I have two monitors on this monitor. Close it all together and open it on that. Okay, well maybe you won't get the video. You can skip the video. Okay, now I have nothing. Wow. I cannot get to that screen. Okay, sorry guys. Okay, I'm gonna reboot the machine because I do not know what's going on. Go Windows. Okay, well, any comments, questions while we're waiting? So my office hours will be Monday at 10 a.m. and it should be on the calendar in a room in Corey. And I know that up until now we really wanted to have office hours right after the lectures, but no one can apparently make it. And so I think they're going to offset that with some other office hours. Hopefully weren't too dependent on it being right after the lecture. We're going to get there next lecture. There are all kinds of differences and benefits, yeah. But that's skipping ahead, so it's not to get totally disoriented, and also because people here are not necessarily up to speed on that. Okay. Wow. This is not the right lecture. Okay, well, if it doesn't work, we're not going to do it. I'm not going to fool around with anything else. Okay, forget it. Okay, that's where we are. It was just going to be a video that actually shows the robot doing this, so hopefully when you download it, if you download the slides, you can see it there. Okay, so apparently in 16A, they don't really use probabilistic models, and they use some other hacky ways to solve this problem. And so because this course has been a lot about probabilistic models, we want to write down a plausible maximum likelihood solution to find the best guess that we can from 3 sensor readings of the position in the plane, which is theta 1 and theta 2. Okay, so again, this is the unknown position we're trying to find an estimate of. These are the known locations of these 3 beacons, so we know them unambiguously with no error. And then these 3 things are the noisy distance measurements, so these are like the data observations we have to work with. So I think it's a good exercise to do this. So everybody just take like a minute or two. I know it says 5, maybe that's too long because we don't have a lot, but try and write down from this problem, like if you want, you can talk to the person next to you, what would be a reasonable loss function, right? So a loss function is something like ordinary least squares or the likelihood. So can you think of a way to write down a loss function for this problem? And so you can just wait until we do it, but it's really, really useful to try these things yourself, figure out, because you get to understand what you're missing, what you don't understand, and it's even, especially if you hit a wall, it's the most useful exercise, because then you realize the wall you hit. Okay, so I'm gonna stop talking and just give you like a couple of minutes to try and think about how you would write this down, where you have these data Ys, you have the known beacon locations, and you want to know the best estimate. You want to formulate a loss function such that when you I'm not asking you to maximize it, I'm just asking you to write down the loss function here. Something akin to, say, ordinary least squares, but this is not ordinary least squares. Okay, go for it. You can assume zero mean Gaussian noise, yes. And you can assume that it's the same for all the sensors. Who wants another 30 seconds? Okay, so let's go through it together. So right, we said we could assume that the sensor noise is Gaussian and that it's the same for all sensors. Okay, so that's an assumption, right? We don't actually know that, but this is frequently when you're setting up a modeling problem, this is the kind of decision you have to make. And Gaussianity, it turns out, is often very tractable and actually works pretty well in practice, but not always. And actually, at the end of this lecture, I'll get to an example where that's not the case. Okay, so I mentioned that what we're getting are these readings which are distances, right? They're noisy measurements of the distance. So we need this notion of Euclidean distance, because that's for like out in the real world on a plane. And so the distance, the real distance between each beacon and the actual parameter is this kind of Euclidean distance. So I'm just defining basically this as a function now. And so now what's the probability here? The probability for one of these sensor readings is going to be a Gaussian in the actual distance, so it's centered on the actual distance, but it has noise added to it, right? So basically the measurement I get is the true distance plus some Gaussian noise. So that's what the example looks like, right, for one sensor. And so the likelihood, of course, for all three sensors is that I add these up because I'm going to assume that they're independent. There's no reason they should be correlated. Does that make sense? Okay, so nothing too tricky, but I think you can probably see already that, like, once I show you this, if I just went through this quickly and I showed you the answer, you'd be like, oh, yeah. But if you have to actually sit down and write it, even quite simple things, you realize that it's not so easy to go from a real problem to writing down the objective function. And objectively speaking, this is a pretty easy version of that. And in some sense, one of the main challenges of being a practitioner in machine learning is exactly this skill. Okay, so right, so the optimization problem we have is basically like this. So it actually looks a lot like what we had before. So it looks a lot like ordinary least squares, but so who can point out what the difference is that's going to make this really hard, that such that we can't actually do ordinary least squares? Like, what's the kind of intuitive thing? I'll just give you, what's that?
Like normally you have like W times X, which is linear, but now you have some sort of like nonlinear function.
Right, so exactly. So where we have this D function here, normally you have here a linear function of the parameters, but now we have this very complex nonlinear function here. So, and because of that, we can't just apply ordinary least squares. And so I'm not going to go through it here, but I would recommend that at home that you try to actually try to solve this and see how you hit a wall and that you can't actually just get those nice solutions. And so this is actually kind of a real problem, but there's many problems that have this property where you can't just kind of use algebra, set the derivative to 0, and get a closed form solution. Okay, so it is a least squares problem, but it's a nonlinear least squares problem precisely because of the nonlinear stuff going on in this Euclidean distance, and that's the key reason that it's hard to optimize. So we're going to have to iterate, which is what I told you in the beginning. And so this is sort of an introduction to iterative optimization in contrast to this sort of like one shot. I shouldn't use the word one shot because it means something else in machine learning, but like the direct closed form, like where you just get it immediately. And so what does it mean when I say iterate? I said it before in the beginning lecture, but just to sort of take you through this sort of a pattern. So there's many iterative optimization algorithms. Some of you may have already taken 127 or heard about it elsewhere, but basically what you do again is you start somewhere in the parameter space, you evaluate where you are according to the objective function, and then you take some step in some direction in parameter space to improve. And if you're done, so the various criteria that you can use to assess that, then you stop, and otherwise you repeat. So this is the core guts of just an iterative optimization algorithm. Of course, I haven't told you actually how to do any of this, so this is just a conceptual thing at the moment.
It's not space convex over here, so can't we just have like optimal solution?
So we're going to get to convexity soon. And even if something is convex, just as a peek ahead, that doesn't mean that you can solve it in closed form anyway. These are not one and the same. So this is going to be a sort of an introduction to what is one of the most commonly used algorithms right now, which is gradient descent optimization. And in fact, when I was in graduate school, this was not the bread and butter of machine learning, but it is right now in the use of neural networks. And it's also just an important algorithm to know. So again, this isn't going to be a whole optimization class, but we're going to give you, because it's such a fundamental part of doing machine learning, we want you to understand a little bit about it so you can get somewhere and know if you want to take more and learn more about this. But so you often see gradient descent shown in different. I'll have different pictures that are used sort of pedagogically to think about it, but it can be applied to anything where we have a loss function that we can take the gradient of. So basically anything smooth, and in particular we can use it for the robot problem I just showed you. And so we can apply to any optimization problem, which means any f of theta, again, as long as it's differentiable. And so what gradient descent is going to do is it's going to spell out how we do this particular step of the general template that I just showed you, which is how do we move from one place in the parameter space at one time point in the iteration to the next point. And so it's based on the observation that if the loss function is differentiable at a particular point, then it's going to increase in the fastest direction of increase. Sometimes in machine learning, sometimes we talk about maximization, sometimes minimization, sometimes you'll see things flipped around, so people do it both ways. But so let's say if you're maximizing, then it points in the direction of the quickest increase, right? And so that's the sort of intuition behind gradient descent. It says, if I use the gradient, this is the direction in which my function most increases, so let me go in this direction. And how much are we going to go in that direction? It's going to be a parameter that we call the learning rate, which is gamma t. And so this is sort of a little pictorial example. Is if you have this simple one-dimensional problem here, and you follow the gradient at each point for some step size, then you're going to kind of keep getting closer and closer to the minimum. And when you're at the minimum, the gradient is of course 0, and so you're now at a stationary point, and you won't move even if you apply this update rule. Does that make sense? Okay. How many of you have seen gradient descent before in another class? Okay. Right, so apparently I just switched notation, sorry about that. So the step size, it could be constant, although as you can see here also there's a subscript t, so it could actually change at each iteration, and we're not going to go into all the different algorithms for adjusting the step size, but there are many out there that you can read about and learn about in other classes. And so I also just want to point out that if you were to move infinitesimally small, so if that step size was like just this, this tiny little thing, then you would always be guaranteed to improve, right? Because sort of locally, that is the point of largest increase, and you couldn't go wrong. On the other hand, if you make that step, and if you make the step size too large, you might actually overshoot, right? So imagine you're sort of following this trajectory. So this is a different version where these are now the level contours of the function that I'm trying to optimize. And so you're following the gradient at each step. But if that thing's too big, then at some point you might just go from here to over here, right? And you might just keep oscillating around here. So I think intuitively you can already see that if it's not too small enough, you're just going to bounce around all over the place. And of course, if it's too small, then you're just going to move really, really slowly, and you're not going to make much progress. And so adjusting the step size it can be kind of an art, and it can also be a proper research endeavor in itself. But in practice nowadays, people use these adaptive step size methods. They're called Adirad, Atom, and we're not going to go into them here, but if you're interested to sort of look ahead, you can Google these. Okay, so for non-convex functions, and we'll get to what convex functions are, we get to local optima, not to global optima, right? This is an example of if we were to start here and we're doing minimization, then we might end up on here, because that's sort of the nearest local minimum. And if we started here, then we might end up here. Is it possible does anyone think it's possible that if I started here, I could end up there? Oh, yes, thank you. Please always tell me. In general, I intend to be using this, so if I'm not, please do tell me. If I started here, is it possible that by using gradient descent that I could end up here?
Yeah.
Yes, okay. How could that happen?
Different running rate.
So how big is step size? So imagine I do like I don't know where those, I wasn't planning the sound effects, but it actually looks kind of like, do you think you could do it with a constant step size? No. What if you had like, right, the answer is yes. There's some schedule of step sizes where you could absolutely do this. Whether it's likely you would ever hit one of those in practice, it's hard to say. But absolutely it could happen. And in fact, so how you get out of local optima and closer to global optima is it kind of also an open question. And a lot of the hacks and tweaks people do is an effort to kind of try to think these things through as best as they can. But all that is to say that the learning rate can make a huge difference, right? So it can affect the convergence, so how quickly you get to a local optimum, but it can also affect which local optimum you get to. And that can be a big part of the game. And so when you look at it this way, you also often hear about gradient descent as kind of hill. I think I heard this from Professor Sahai, who I think heard it from someone else, but it's this analogy of hill climbing with fog. So at any given point, you're in this like mountainous terrain, and the fog is around you. Why do we say the fog's around you? Because all you have is the gradient right there, right? You can't see the gradient over there or anything else. You just have your sort of very local information. This is in some sense a very greedy algorithm, right? You just say, I know this is the best place to go here, so I'm going to go like that. And then once you're over there, now you can see a little bit further, but you still have only local information. And so I think it's sometimes a nice way to think about it. Okay, so what kind of points can gradient descent land on? So obviously anywhere where the gradient is 0. If we run into some convergence criteria, the idea is that it's going to be where the gradient is 0. And so these could be minima, they could be maxima, and they could be global or local, right? So it could be any of these. What else could it be?
Oscillate.
Could be a saddle point, and it could be an inflection point, right? So you remember this from first year calculus. Inflection point is when it goes from like concave to convex. And saddle point is where basically you have in one direction a minimum and in the other a maximum. And so in general, in machine learning, we're kind of never interested in inflection points or saddle points. We're always interested in either a minimum or a maximum. And ideally the global, but we can basically never have a guarantee, rarely can we have a guarantee of global unless some properties occur. Right, so how do we deal with the fact that we only want one of these stationary points, so typically a maximum for maximum likelihood, although sometimes you'll see people minimizing the negative log likelihood. This is just somehow a convention. But there are some classes, as was alluded to earlier, of functions that we don't need to worry about this. And these are convex functions. And in convex functions, there's only one minimum, right? And so basically, this is sort of a classic example to explain a convex function, but roughly speaking, if you connect any 2 points, so these are 2 points x, and this is where they evaluate to f of x, then if you connect them with a line, it stays above the function. So that's the sort of very intuitive definition of convexity. And so this was a good one from Professor Sahai that I never heard. I don't know if he came up with this one, but I also have problems remembering convex versus concave. And so he says concave looks like the entrance to a cave. And so now actually I will never forget it. I always forgot this. Who's heard that one? Anyone? Is this like, okay, so did you hear it from Professor Sahai? Did you hear it in a course here? All right. Did you dream it at night? Where did you hear it from? You don't know. All right, no worries, no worries. Okay. So formally, you can write this convexity down like this, and strict convexity, for which the difference is just the difference in strict inequality or not. But basically, what it says is that the linear combination of, so here the t lies between 0 and 1, so this is a linear combination of 2 points at which we're evaluating things, that the linear combination, a function evaluated at the linear combination is always less than or equal than the linear combination of the function evaluation. So, but I think the easiest way to think about it is just that if I have these 2 points and I draw a line, that it always stays above the curve. And so I think if you sit and think about it, for these kinds of functions, there is only one minimum. And so if you apply gradient descent, you will definitely get there, right? So gradient descent will take you to the global minimum of convex functions, assuming you run it long enough and with a step size that enables you to converge. And so actually, strictly speaking, that people don't always talk about this, you actually need the domain, so X to also be a convex set. There's a sort of analogous definition kind of analogous of convexity, which is you have a set of points and you take any 2 points and you can connect them. All the things along the connection are also in the set. And so if it's not convex, it's basically a concave set. And so in order to have this guarantee of a single global minimum, you need to have a convex function on a convex domain. And then this is sort of we're not going to do too much with this in this course, if anything, but just so you know going forward that you can even do gradient descent when you don't have a completely smooth function. So you can't have some arbitrarily crazy function, but imagine you have kinks in the function. So you see these kinks here, right? So at the points of kink, there is no gradient defined, right? It's a non-continuous function there. So can you guys think about imagine we're doing gradient descent and we land on exactly one of these kinks. Like what could we do in order to keep moving forward? Is there some vector, some tangent plane that maybe is intuitively acceptable that will allow us to keep moving on? Yeah? Well, that's a nice one, yeah. So the suggestion was like take some sort of box around the point of interest, compute the gradients there and average them. Yeah, that's a great idea. And in fact, that would be related to this idea of subgradients or subderivatives. And so these are basically what you would think of as a reasonable version of a gradient that you can use. And this is the formal technical name for them. And basically, it's any of the vectors that, or the directions that lie kind of constrained by either of those two planes, right? So I can't go past this one and I can't go past this one, but I can kind of go arbitrarily anywhere within that range. And so in fact, technically the subgradient is any one of these infinite vectors that kind of adheres to this constraint. So basically the steepest it could be is like this blue line here, and the least steep it could be is like this blue line here. Those are the constraints. And anywhere within there is a valid subgradient. And so you can just use that. Okay, so gradient descent typically doesn't get used in its sort of vanilla form, which is the form I've roughly described now. And so sometimes it can do really weird things. So here you can see that the minimum is here, and so we want this trajectory, these little arrows to be going here, but they're following the gradient in these small steps, and they're doing something wacky, is they're kind of going like this. Or, I mean, you can see. So can anyone take a guess as to, like, what's the fundamental property of this objective function based on these contour lines that's causing a problem? So it turns out it's from what we call sometimes the local geometry of this function. And so by the local geometry, we mean basically the curvature, like what is the shape of these level sets of the function? And the Hessian, of course, is what describes these. And so when the condition number of the Hessian is really bad, so in other words, when the largest eigenvalue over the smallest eigenvalue has a really big number, it means I get these very sort of drawn out ellipsoids, right? And when that happens, then I have this kind of wonky local geometry, and this is the kind of thing that easily screws up gradient descent. You can take a look after very carefully and see that actually this, I believe, I didn't draw this, but I believe this is literally following the gradient, and yet it does this weird thing, and it's because of this very sort of skewed ellipses that you get. And so the closer they are to round, then the better the behavior will be. And in fact, many techniques that we won't get into here are trying to take this into consideration, and we'll kind of allude to some of that now. Yeah, question?
Yeah, it's like this one eventually get to the right.
Yeah, it will. It should still. Well, okay, if it's convex, then yes, it will. Right? This could be. I mean, this could very well be a convex function. We can't see outside. This is just sort of the local neighborhood. So absolutely, it will. But it might get there kind of like arbitrarily slowly. And so it may be of no practical utility. And the worse the condition number, the worse that is. So it basically has a strong effect on the convergence. And so it's good to understand like these things, like what is, even though I'm following the gradient, I have a reasonable step size, like am I okay? Well, actually no, not necessarily. And so what I just sort of said is that second order methods, so gradient descent is a first order method, it's using the first order derivatives, right? But if you use the second order derivatives like the Hessian, then the Hessian actually tells you this curvature, and if you know the curvature, then it stands to reason that you can do something to mitigate this problem. And so we're going to talk a little bit about that, but first I want to just show you that on real problems, like, and again, anchor it on this robot localization problem, that here this is actually not a convex function, and that it has multiple optima. It has, of course, it has one global optima, and then it has several local ones. So let's just try and think about how we can, again, this is another important thing, like a skill to have when doing machine learning is, one is like, how did I formulate that problem, which we just did, and then try to understand at an intuitive level just by thinking. I mean, you can't always do this, but it's good exercise to try to think about things and see what you can understand about your problem before you try to tackle it. And so we have this optimization problem, and I apologize, but I just noticed this right before I changed the anchors to X here, where they were L before, but so we have these beacons. So these are the two beacons, and let's just do sort of one dimension. We have one location here, one beacon location here, and we want to know where now on a line, not the plane, the robot is. So if you think about this, and again, I'm just going to maybe give you a little, actually maybe we're running a bit low on time, so maybe I'll just actually walk you through it. But so what happens? Imagine I have just one measurement from the first beacon. So what does that measurement give me, right? It gives me a distance to the robot, a noisy distance, and that distance is y1. So what that means is that it's telling me with equal probability the robot might be here, And it might equally well be here, right? It has no way to distinguish. It just says, I know I'm this far away from the robot. Okay, so that's with one sensor measurement. Now, if I measure the second one, imagine that I didn't measure the first, and I'm going to draw a similar one for the second. So, so now just the green line is what would happen. So this one's further away, and it gets this larger thing. And so now, according to just x2, if it has no knowledge of x1, it believes the robot might be here, or it might be here with equal probability. Now, of course, when I combine these, then I get rid of the symmetries, right? So if I put them together, and then I look at the likelihood, and I look at where the peaks are, what's going to happen is it's going to, and with more and more measurements, and depending where these beacons, how the beacons are aligned relative to where the actual robot is, this thing is going to start to get bigger and bigger, right? So because there's far more evidence over here because the red and green kind of overlap, right? So this peak in the likelihood will be much higher, and this one will be lower, and this one will be lower. But of course, if we're doing gradient descent, and we start our parameter out over here, we might end up here, we might end up here, we might end up here. So this is, again, this is like a pretty simple example where already you have these multiple maximums, right? And so this is like, and you can imagine on much more sophisticated problems that this can just become super, super crazy. Okay, so how could you, if you want to know if your function is convex or not, what can you do? Well, if you can show that like in one dimension that the second derivative is greater than 0 everywhere, then you're good to go. And correspondingly, in multiple dimensions, if the Hessian is positive semi-definite, then you also have this convexity. And so, or you can also use the definition of convexity that I put up on the last slide to try combining different convex functions in different ways and manipulating the math to see if you can still get it to look like it's convex. So these are the kinds of ways that people might prove convexity themselves. Although I'd say in practical day machine learning, many models are not convex, and we kind of just know that, and we don't bother to do this, but it's good to understand what things are closed under convexity and things like this. So is linear regression a convex problem? How about ridge regression? What do you guys think? Yeah, they are, right? So we just get this nice closed form solution, and if you check it, it should be convex. And so, and in fact, convexity, one thing that's good to know is it's closed under non-negative linear additivity. So if I take regular, just ordinary least squares, this is convex. And then if I add a penalty, like a ridge penalty, which turns out to be convex, or any other convex penalty, and I add it with a positive weight, then this whole thing is also convex. And so I maintain the convexity there. So it's good to know how you can mix and match these things. Okay, so how do we deal with convexity in practice? So, and again, especially one of the common places we want to do this is neural networks, but actually even I didn't even use neural networks for much of my career, and still we do this all the time. And so what we do is we do multiple random parameter initializations. So, in the robot localization, maybe you just use a random number generator in some reasonable range, and you generate the first initialization, and then you follow the trajectory of where gradient descent takes you, for example, and then you do another one, or maybe you have access to a cluster, so you do these in parallel, and then you just compare them, and you take the best one. And if some of those are weird inflection points or stationary points, then they're not going to win the competition, right? So that's actually, people kind of, in some sense, kind of ignore all the technical stuff, and they just run it many times, and then they take the best one. And so how many should you do? Again, like, you know, it depends how much time you have, but I guess you might want to do as many as you can, but sometimes you do a bit of a sensitivity analysis to say, like, is it tend to converge to the same thing, even when I put these things, like the initializations further away, and if you get a sense that it has sort of it's behaving nicely in practice, even though it's nice convex, maybe going forward in your experiments, you only do a few initializations or something like this. Okay, so how do we know if we hit the global maximum? So we don't, right? Actually, basically almost never know, and still that gets us pretty far. And in fact, I don't know if we'll get into it in this class, but in modern day neural networks, you actually basically don't ever want to hit the global maximum. And that's maybe going to be counterintuitive for everything we talk about in this course, but those are weird models that actually contradict a lot of the traditional wisdom in statistics and machine learning. And we won't have time to go into that, but in that case, you often do not want to get to a global optimum because these have sort of overfit the data. and you'll get to some weird point that doesn't generalize well. Kind of wacky and interesting. Okay, so back to this problem here. So the point of bringing this up in the first place was to say, here's an example of a nonlinear model emerging in a kind of real world situation. And then it motivated us to look at gradient descent. But actually, if you look at this problem, right, I said this actually has a name, and it kind of has a name for a reason, this nonlinear least squares problem. And the reason it has a name is that it has a specific structure, and it turns out we can actually leverage this structure to do something different from gradient descent that might actually work better, and generally should work better. Right, and again, just to emphasize, this R, sometimes we write R as the residual, right? Because the difference sort of between what you might think of as a prediction and the actual, or sorry, this is, I guess, well, the robot localization doesn't work very well, but usually this is like the prediction of, say, the model, and this would be the actual data. But in any case, again, it's because this is not a linear function of theta that things get complicated. And so, but we could use gradient descent, and that's why we started with this example. But we can also exploit this quadratic structure of the residuals to do something different. So let's go through that. So what if we did the following? It's nonlinear, but at every iteration, we could take the best linear approximation to the residual and then do ordinary least squares. And so even though it's an approximation, that might work really well, right? And so you probably all in first year calculus saw this sort of Taylor series expansion, at least in one dimension. And that's basically how we get the best linear approximation, or if you get higher order terms, the best quadratic approximation, and so forth, right? And so what we're gonna do is we're gonna say that this residual now, which is a nonlinear function, because we're in nonlinear least squares, we're going to linearize it by doing a Taylor series expansion around the current parameter estimate, theta t, right? And then we're gonna get a delta theta. So that's just for one of the residuals, for one data point, like one of those sensors. If you want to write it out in vector form, then this is basically the Jacobian, where you have each R is sort of a separate part of the function, and then each theta has its own component, so this is a matrix. And so now what we want to do is we want to do, again, sort of what we call roughly maximum likelihood estimation, or it's really nonlinear squares, and we want to find, again, the max of this with respect to theta. But when we look at it now, oh, this typo, this should actually say, down here, the max of delta theta. We're solving for delta theta, that's the point. We know theta t, and we want to solve for delta theta. And actually, this looks can you guys see? This actually looks just like ordinary least squares, just with some other symbols there. If I were to correct that, I'm scared to touch the laptop, so I'll correct it after. Right, so in fact, this term here, the Jacobian times delta theta, this is like x times beta, right? Or x times w. This delta theta is the parameter we usually think of solving in ordinary least squares, and this Jacobian is playing weirdly the role of x, right? Because usually this is y minus x times beta, and so this is x. This is the parameter we're solving for, despite the typo, and this is what we can think of as the observations, except it's actually the residuals using the previous parameter estimate. And so given that mapping, then we know what the solution is, right? And we can compute a solution in closed form now because this actually is ordinary least squares because I linearized the problem. And so what I end up with is this, right? And this, again, this maps exactly to ordinary least squares. This is like x transpose x all to the inverse times x transpose times y. And now, of course, I don't actually really want delta theta. So delta theta is actually just the difference between where we want to go and where we are. And so that gives us the parameter estimate. It says take the previous parameter point and increase it by this. So this is obviously quite different from gradient descent. And it's because what we've done is we've linearized this thing that was nonlinear with a Taylor series, and then we said, given that it's linear, let's use ordinary least squares. And now we move ahead, and we do this linearization again, but now we do it at the new parameter estimate, right? So every time we move in the parameter space, we again make this linearization approximation, and then we move forward. Any questions on that? Okay. So this linearization approach that's tailored to non-linear least squares is actually called Gauss-Newton. And what's kind of interesting and not obvious at first glance is that this is considered a second order method, even though it's only using the first order derivatives. And actually, when I first saw this, it was hard to dig out even why that was. And so because that's so puzzling and people say it, but they don't ever show why, I just grabbed some slides to just show you kind of quickly. I'm not going to spend too much time on it, but just say, why is this a second order method if all I've used is the Jacobian, which is a first order derivative? Does anyone have any just intuitive guesses? So it's going to turn out that this term, which comes in the method, the Jacobian transpose the Jacobian, is actually a really good approximation to the Hessian for these problems. And the Hessian actually is a second order derivative. So in some sense, what we're getting out of this is an approximation to the Hessian by using only the Jacobian. And so this, right, so this here actually is sort of like the Hessian inverse. And that's actually why this might work better than gradient descent, because it's now has an understanding of the curvature and it can correct for it instead of doing this really, really slow convergence. And so I'm going to walk you through this really quickly, which is, so why is this thing the Hessian? So you have this setup like this with these, the function is a sum over these residuals. And the Jacobian is where the parts of the function are R1 through Rn, and then now the parameters in this notation, sorry, are Rx. Basically, if you take the gradient, it ends up looking like 2 times the Jacobian times the residuals. The Jacobian, again, is this matrix, so the gradient here, this is where I've summed over all the different R's. So this says dimension number of parameters, which is the length of X, and it uses this Jacobian. And so this is sort of one key thing to remember. And then, after that, if we want to get the Hessian, then we take the derivative again of that expression, and basically, I know I'm going fast, I just want to kind of give you the intuition, and you can look at it in more detail after, but take the derivative again of that, you end up with 2 terms. You get this, and you get this. And the first one is 2 times the Jacobian transpose Jacobian. This is the thing that I said is a pretty good approximation to the Hessian, and that's because the second term here, it has this dependence on the residuals. And if these residuals are small, then this term is small. And at the very worst, these are typically 0 mean, and so this term in general often ends up being quite small, which means that this term here, just the Jacobian transpose Jacobian, is a pretty good approximation to the Hessian. And so that's why Gauss-Newton is this sort of second order method almost for free, in that sense it only computes the Jacobian. Okay, so, but that was very specific, right? This Gauss-Newton thing was only for nonlinear least squares. So what if my thing here does not look like nonlinear least squares? It's just some arbitrary function. So do you think there's anything I can do? Is there some sort of similar kind of approximation I might think of making that will let me get somewhere? Any suggestions? Okay. So we could, of course, do gradient descent again, assuming that this is smooth enough. We can always do gradient descent. But again, we can also do something else, and this something else is actually going to end up also using the curvature, although in this case, we're going to have to explicitly compute the Hessian. And that's because that nice approximation to the Hessian fell out only because I had non-linear least squares, right? It was very specific to that exact objective function. If I have a general one, I can't use that trick, but I can also do an expansion. Turns out I'm going to have to do a quadratic expansion, and I'm going to have to actually compute the Hessian. Okay, so let's just go through that a little bit. So supposing we're at theta t, and we want to expand out our function using a Taylor series expansion. So imagine that we were just going to do a first order expansion like we did last time. And we have this thing here, and we want to set the gradient of this with respect to delta theta to 0. Then what's going to happen? The gradient of this is just going to go away. The gradient of this with respect to delta theta will just be this term here, which is a constant. And so we have no way to set the derivative to 0, right? So I'm stuck with a constant. I have no way to move to make the derivative 0. So basically, this is a dead end. I cannot do a linearization and make progress. So I need another term to the expansion, and then I can do something. And that's where we get to the Hessian, is we're going to do a second order expansion. So instead of just having these two terms, we're going to add a term here, which includes the Hessian, right? This is just now taking the Taylor series truncation one out further, so I have the second order derivative. And what I'm going to do is I'm going to do the same trick I did before. I'm not going to go through it line by line here, but I'm going to take the derivative of this with respect to delta theta, and I'm going to set it equal to 0. So what am I doing here intuitively? At every point, as I'm moving in my iterative optimization, I'm not making a quadratic approximation around the current parameter estimate, and then I'm going to solve for that by setting in closed form the gradient to 0. And so take the derivative of this, set it to 0, and solve for it. And so I won't go through the steps here, but it looks like this. And here we get the inverse of the Hessian. And so again, this is now a truly proper second order method, because it has the Hessian. And again, right, we don't really care about delta, we want to know how to move, so we start with where we are, we compute the Hessian at that point, we compute the gradient at that point, and we apply this update. So, does that make sense? Okay, so just to recap, like we could just apply gradient descent, which just says follow the gradient at some step size. And then we said, if we have the specific structure of nonlinear least squares, we can do something a bit more clever with the gradients, because it turns out the Jacobian's like the Hessian, and we can derive that by making a linear approximation at each step and solving for delta theta. But now if we're in the most general case where we don't have nonlinear least squares, with that linear approximation doesn't bias anything, so we need to do a quadratic approximation, and that's why we need to actually compute the Hessian here. And so that's actually pretty expensive, right? The Hessian is a big matrix, which you need to spend more time computing. And we won't go into it in this class, but there's a whole bunch of techniques people use where they essentially accumulate information over iterations to make it cheaper and things like this. And in fact, nowadays, I would say not too many people are using second order methods, at least for neural networks, because just gradient descent and variations of it work quite well. Well, in some weird way, you can think of this as a version of gradient descent, right? Like you're computing the gradient, but you're kind of, what are you doing here? You're kind of correcting for the weird curvature in the space, right? H is basically that curvature of that weird thing. And in a sense, what I'm doing is I don't want to get screwed up, and so I'm going to kind of somehow unscrew it up by using that curvature. That's a kind of intuitive way to look at it. Right, okay, so who can think of some function for which I can do just a single step of this Newton's method, and in one step get to the global optimum? Like certainly it has to be convex, but what else? Is it possible? Is there some function where I can do just one step and I'm guaranteed to get there? A constant. Well, a constant doesn't really have them, I mean, it's just flat. So that's like a. Yeah, okay, that's true. All right, fair enough. How about a function that might plausibly be useful? N has this property. Yep. Convex quadratic, right. I mean, if it's quadratic, I guess it is convex, but yeah, that's right. So if it actually is quadratic, and we make quadratic approximation, it's actually not an approximation, right? It's exactly the right thing. So you have this quadratic thing, and you actually just move directly in one step to the global optimum. So that's, I mean, you're not likely to be in that situation, but again, it's useful to always think these things through, just to, it gives you some understanding of what's going on, right? Okay. So, right, so, okay, so far we talked about vanilla gradient descent, and I'm gonna just give you one other variation of gradient descent, because this is the one that is most commonly used, and we're not gonna go too deeply into it, but so far we've been computing the loss and the derivative and everything using all of our training data, right? Like no one's ever suggested we should do it on half or something like this when we're doing training. I mean, there's a notion of splitting things up in cross-validation, but given that you have some, imagine you've already split up your data, and these are the data you're going to use to train the model. Like everything we've done in the class, we always use all of these data, right? So if we have n training data, then this is gonna scale linearly with n at the best, and sometimes worse. So, and n can be in the millions for some kinds of data, and in particular, again, for neural networks, these are very, very data hungry. They're actually, in some sense, terrible models. They're like they need so much data to do anything, but if you give them a crazy amount of data, then they're powerful. And so, the question is, could we use a subsample of the training data to do this? And so this is what takes us to stochastic gradient descent. And this isn't always valid, and I'll actually tell you, when I interview people for grad school and things like this, one of the questions I ask them is like, when can you apply stochastic gradient descent and have it be valid, and why? And almost everyone gets it wrong, even though it's somewhat simple. So when you do maximum likelihood, if you have these independent terms, like as the noise or IID, then you get this summation of losses, right? And really what that is like an expectation over your training data of the loss. So I'm just rewriting the sum as an expectation. And because you can think of it that way, then by linearity of the gradient and of expectation, then I can actually also say that the gradient of the loss is the gradient of the expectation, is also the expectation of the gradient. So I'm just interchanging the expectation of the gradient. Okay, so far I haven't used fewer samples. I'm just rewriting things in an effort to motivate why we can use fewer samples if we want to. So this is, right, I started with my loss function, and now I've just sort of through different, it's a different way to write it mathematically. It's an expectation over my training data of the gradient. Okay, great. So what that means, though, is because it's an expectation of the training data, it means that if I use any subset of those samples, it's going to actually give me an unbiased estimate of the gradient. So, right, whatever subsamples I use, like they're all going to be unbiased. So they won't give me the gradient, but they will be unbiased. So an expectation, they will be the gradient. Right. This is the technical term for meaning that it's unbiased. So, and so what we can do is we can approximate the gradient with fewer samples, and this is what we call stochastic gradients. And when you use this in gradient descent, this is where we get stochastic gradient descent. And so it's gonna look the same, right? Like I'm gonna just move in parameter space, but now I'm going to take the gradient with respect to a subset of samples S. Okay, and so this could be much, much faster computationally, right? Like if I compute it with only 10 samples instead of 10 million, this is faster. But is like, do we shoot ourselves in the foot at all? Well, that depends. But just so David Bly, this is a courtesy. This analogy courtesy of David Bly at Columbia. Was a really funny guy. If you ever get a chance to hear him talk, you should do it. And so he calls stochastic gradient descent inebriated gradient descent. And so he thinks of it this way: is that you're kind of like at some restaurant and you need to get to your hotel, and with regular gradient descent, you get a clean estimate of the gradient. And if you have a well-behaved local geometry, then you're going to get there pretty quickly, right? Pretty smoothly, pretty directly. However, if you do this thing that I just called stochastic gradient descent, then depending on how many samples you have, you're going to have a pretty noisy estimate. And so on average, you're going to go in the right direction, right? So eventually you should get there, but it might take you a lot longer because you're going to kind of stumble this way, and then you're going to stumble that way. And so it still works, but it could be sort of a very long way to get there. And so in some sense, that's kind of intuitively the trade-off is you can do things more cheaply computationally, so each iteration is much faster, and so you can compute more iterations, but at the same time, you've introduced noise into it. But you still get you can get guarantees, absolutely strict technical guarantees of convergence because precisely of this unbiasedness property. And so you might ask, like, well, what's interesting is how does the variance depend on the number of samples? This is sort of the thing you want to know. And I think intuitively you can imagine that the more samples we have, that the lower variance the estimate of the gradient is, the less noisy it is, and the less you have this sort of moving all around, right? So if you just go through what that is, basically, when you pull out this 1 over S out of the variance, you have to square it. And then you have the variance of a sum of independent random variables, so you just get S times the variance of each of these. And so altogether, it basically just gives you 1 over S times the variance of the gradient. And so the more samples that we use to estimate the gradient, the lower the variance of that stochastic gradient. I think that's pretty natural, right? Like at some point, if we're using all the training data, then actually there's no variance. That is actually the true gradient with respect to the training data. And so you can see how this plays out in a picture here. So S is the number of samples that you use in each computation. And so I won't go too much into details, so you might just pick random samples to compute the gradient with, or more likely what you do is you take your training data and you put it like into batches, and each one you compute the gradient with this, you move, then you take the next chunk and then you move, and the next chunk and you move. And so you can see here that if you have a huge number, imagine that's the total number of training points, then again you get this nice smooth trajectory. And if I use a smaller set of samples to estimate the gradient, then it's noisier, then it's gonna still go in the right direction, but like kind of a bit more wonky. And if I only use one, which is pretty crazy, like it could take forever basically to get there. And you have to be really careful, more careful with stochastic gradient descent about the learning rate. So we're not gonna go into the details of the convergence rates for these algorithms, which you can see in other courses, but there are some constraints both for gradient descent and stochastic gradient descent on what learning rates allow you to converge, and it's a bit trickier here because of this stochasticity. And so you actually need a learning rate that decreases. And you can imagine why, right? Is you have this noisy gradient, and if the learning rate's not decreasing, you're just gonna be bouncing around based on that noise. At some point, you get as close as you can to the local optima, and then you just have all these noisy gradient computations. You can never quite get there unless you systematically reduce the learning rate. Whereas in regular gradient descent, that's not true. For some set of learning rates, you can have a constant learning rate and still converge. So just some things to think about is that fewer samples means you have a higher variance estimate, and therefore it might be slower convergence in terms of number of iterations to a local optimum. But also some people argue, and it's a little debatable, but maybe it also gets you can imagine it accidentally shoots you into a sort of different area, and you actually get to a better local optimum. And there's this trade-off of accuracy of the gradient and speed of the computation. And then something also we're not getting into, but just so you can, like, if you're interested, you can also start exploiting things related to computational efficiency. So if you have little batches, you can imagine that you can parallelize it, and then maybe somehow even in one step, you might parallelize and somehow combine them. You can also make use of vector operations and GPU processes to make things faster, just by the structure of doing it this way. So just to give you some terminology, because you'll hear this, so batch gradient descent refers to using all of the samples in your training data. So that would give you batch gradient descent is just regular gradient descent. Mini batch refers to using fewer than all samples, and the mini batches are each little batch you use to compute the stochastic gradient. And you can, as I said, you can select the samples at random, or you can typically more likely partition them into folds. And so imagine these are your training data, and then I chunk it up, and I start with this, and then I go to this, and go like this. And then by the time I'm done all my data, we usually call this an epoch of training. So however many partitions of my data, that's how many iterations you do in one epoch, and then you train for many epochs. So reasonable, I mean, it's hard to say, but just to give you a sense, like sometimes people might use like 100, like if you're just spending a ballpark number, but you know, this can vary for many reasons. Right, and so, okay, so, and I already sort of emphasized this, so right, so that's it for stochastic gradient descent. This is the thing that's most commonly used in neural networks, but to be clear, neural networks are not the only things that are used in modern day machine learning on real problems. I work on real problems for my research, and I use them, but I also frequently don't use them. But in any case, if you're interested in going on in machine learning, I highly recommend you take more optimization courses, and I think this is the first one in the set of ones that can be taken here. How many people said they took this already? I think sometimes it's listed as a prerequisite. It's obviously not an important one, but that's good. So who here took 127? And I think you've learned everything I just said, except maybe SGD. I'm curious, is there anything in here that I said that you didn't learn in 127? Anyone? Oh, today, I see, okay. Got it. Very good. And so also, right, I just wanted to emphasize this, I said this at the beginning, which is that formalization is like really about, so you take some problem, right, the robot, you have some data, and you have some stuff, and like, and someone says, go do this thing for me with it, right? And so I think one thing you don't necessarily get a lot of exposure to in this class, but is really, really important, is understanding how to formulate the problem. That's why, like, I gave you a few minutes to say, like, just think about what the objective function looks like, because in some sense, that's like that's actually like the most intellectual part of the endeavor, right? Like, once you know all these routines, you know SGD, you know this, like that stuff, at some point you know it and you know it cold, and you deploy it, or you try this, you try that. You can never systematize taking a real problem, like you'll have on a job one day, in research or in industry, and turning it into a machine learning problem. And so, especially, I work at the intersection with biology, so for me, often this entails like an iterative conversation with like wet lab scientists, actually in the chemistry building and the biology building, and so, and that can be a lot of fun. And also, sometimes, you know, people tell you stuff about your problem, and you might try and like completely model it absolutely perfectly, but in some sense you can never actually do that for two reasons. Because perfectly usually means, like, and if you take it to the limit, it means modeling things atom by atom in the physical world. And even if you take it less literally than that, for the complexity of what a real world problem is, you don't usually have enough data to warrant such a complex model. So there's always this sort of knob of like, well, I know this isn't quite right, but nevertheless, I'm going to formulate the problem like this and see how it works. Maybe then I try something a bit more complicated and see how that works. Okay, so we have a few minutes. I'm just gonna, this has never been presented in 189, but I think this is really cool, and I just wanna give you, like, this is actually from some research papers, and I just wanna give you a sense of this. So it'll be a little bit quick, but so far, we've always assumed Gaussian error residuals, right? And so, and I said often these are pretty good. In fact, almost always, like most people in the world make this assumption. It's very common, but are there times where we might not want to do that, where that's not quite good enough? So it turns out there are. And so these figures I'm showing you are from a colleague of mine who works in genetics. We worked together for many years doing statistical genetics and machine learning for genetics. And so there you're often trying to predict things like traits from the genetics, and maybe like what's the probability, or like what's your blood pressure, given that I measured this like a million parts of your DNA. And so when you do this, people typically use a Gaussian model. But as you can see here, if these were the data, like it's not quite Gaussian, like the Gaussian is not quite right, and this is actually more Gaussian. And so the way you do that, in this case, is you take a log transformation of the data. So if you've ever done some like sort of research stint on real data, you might have, in a lab, they might have said, oh, take the log of this before you do your regression. So that's kind of what that is, right? But that's not the only transformation, and it's not necessarily the best transformation. So maybe you take the log with that base, maybe you do this, maybe you do that, like there's a whole bunch of these, and you don't actually know which one to do. And so the motivation for this work that I'm just telling you about, just to give you a sense of like some stuff that's out there, but very related to the course. So in this paper, also for genetics, what they did is they just tried all these, they listed by hand a whole bunch of transformations. This is like the antithesis of machine learning, right? And this is actually how it's done, like all over the world. This is basically what you do is you take like a whole like kind of library of these things and you try each of them, and then you assess how well, and you pick the best one, and then go for it. Okay, but we're machine learning people, right? Like we can do better. So how can we actually choose the best transformation? What does best even mean? And should we restrict ourselves to this sort of like family of things? And so there's this cool work out there. There's a few different papers about it where, and again, I know I'm just going quickly, I just want to give you a sense of this, but what you do is you take your regular regression label, so maybe this was the, I don't know, what were examples we've been doing, I don't know, but like, let's say that was your blood pressure, and you're trying to predict it from your genetics. What you do is you pipe it through a function, and in fact, a non-linear function. So now we have a non-linear model, and then these are the transformed ones, and the idea is you want to make these look like they're Gaussian. And you're going to learn parameters of a transformation that make it look Gaussian rather than this nonsense of like just trying a whole bunch of stuff. And so what is that going to do? You're going to get this big multivariate, I mean, depends on the model, but this is the model that they're using, a big multivariate Gaussian, basically. And so now they call it the warped log likelihood, because they call this the warping function. This is what I talk when I say warped linear models. This is what I mean: is you're trying to warp the things you've measured, the regression labels, such that it better adheres to the assumption of Gaussianity. And so when you do this, you essentially, when you pipe it through that function, you're doing a change of variables, right? A nonlinear change of variables. And so you have to correspondingly add a term, which is for the change of variables, which is the Jacobian, which you should have also learned in first year. And so now you have, the idea here now is that when you're doing your iterative optimization, which you're going to have to do now because there's no way you can do it in closed form unless you put something really simple here. So now the goal is you learn the beta and the parameters of the transformation that make the data look Gaussian, which I think is pretty cool. And what might you use for these warping functions? So one thing that's used is you want them to be monotonic and flexible. And so in this example, you just have a bunch of tan h's, each of which is monotonic, and you have some parameters so you can sort of shift them around and stuff. And altogether, this gives you like a very flexible warping function. And so that just has stuff like step size, steepness, position, and things like this. And so there is a Python demo. I restarted my computer, so I guess it's lost. Never mind. I'll try to put it up if Nicola lets me do that. But so if you want to see more about this, like the paper I just took this from is from my friend Nicolo, who was a colleague of mine at Microsoft and worked a lot together, although not on this. And these are these warped linear mixed models. And then that work actually was developed based on this other thing called warped Gaussian processes. So you obviously don't need to read these, but if this is interesting to you or you're doing some research and you want to know more about it, you can look there. Okay, end of lecture. Next.